Welcome back to this lecture on direct current charging or DC charging of electric vehicles. In this lecture we are going to learn about three things. What are the key parts of DC charger? What types of connectors are used for DC charging? And what are the limitations of DC fast charging? First of all, let us have a look at what are the key parts of DC charger. DC fast chargers typically operate at level 3 charging powers and are designed to charge electric vehicles quickly with electric output ranging between 50 kW up to 350 kW. With high power operation, the AC-DC converter, the DC-DC converter and power control circuits become larger and more expensive. That is why DC fast chargers are implemented as an off-board charger rather than the on-board charger, so that it does not take up space within the vehicle and the fast charger can be shared by many users. Let us now analyze the power flow for DC charging from the DC charger to the EV battery. In the first step, the alternating current or AC power provided by the AC grid is first converted into direct current or DC power using a rectifier inside the DC charging station. Then, the power control unit appropriately adjusts the voltage and current of DC-DC converter to control the variable DC power delivered to charge the battery. There are safety interlock and protection circuits used to energize the EV connector and to stop the charging process whenever there is a fault condition or improper connection between the EV and the charger. The battery management system or BMS plays a key role of communicating within the charging station to control the voltage and current delivered to the battery and to operate the protection circuits in case of an unsafe situation. For example, controller area network, shortly referred to as CAN, or power line communication, shortly referred as PLC, are used for communication between the EV and the charger. Now that you have a basic idea of how DC charger is configured, then let us look at the main DC charging connector types. There are 5 types of DC charging connectors used globally. The CCS Combo 1, which is mainly used in the US, the CCS Combo 2, which is mainly used in Europe, the Shademo connector used globally for cars built in the Japanese automakers, the Tesla DC connectors, which are used for AC charging as well, and finally, China has their own DC connector based on the Chinese GBT standard. Let us now look at them one by one. The Combined Charging System or CCS connectors, also referred to as combo, are integrated connectors from both AC and DC charging. They are derived from the Type 1 and Type 2 AC charging connectors by adding 2 big extra pins from high current DC charging. The connectors are respectively called Combo 1 and Combo 2. Let us first look at the CCS Combo 1 connector. In this slide, the Combo 1 vehicle connector is shown on the left side and the vehicle inlet is shown on the right side. The vehicle connector of Combo 1 is derived from the AC Type 1 connector and retains the earth pin and the 2 signal pins, namely the control pilot and the proximity pilot. In addition, 2 DC power pins are added for fast charging. On the vehicle inlet, the pin configuration in the upper part is the same as AC Type 1 connector for AC charging, while the bottom 2 pins are used for DC charging. Similarly, the CCS Combo 2 connectors are derived from the AC Type 2 connector and retains the earth pin and the 2 signal pins, namely the control pilot and the proximity pilot. 2 DC power pins are added at the bottom for high power DC charging. Similarly, on the vehicle inlet side, the upper part facilitates 3-phase AC charging like the Type 2 connector, and the bottom 2 pins are used for DC charging. Unlike Type 1 and 2 connectors that uses only pulse width modulation or PWM signals on the control pilot, power line communication or PLC is used in both Combo 1 and 2 chargers on the control pilot. Power line communication or PLC is a technology that carries data for communication on the existing electric power line, which is used simultaneously on the power transmission as well. The CCS charger can deliver up to 350 amps at a voltage of between 200 to 1000 volt, giving maximum power output of 350 kilowatt. It must keep in mind that these values are continuously updated to cater the voltages and the power requirements of the new electric cars. The third DC charge type is CHAdeMO, which is a Type 4 EV connector and has 3 power pins and 6 signal pins. CHAdeMO uses a controller area network or CEN protocol in communication pins for signaling. A controller area network communication is a robust vehicle communication standard designed to allow microcontrollers and devices to communicate with each other in real time without the host computer. As of now, the voltage, current and power levels of CHAdeMO are 50 up to 500 volt. In the future, it is expected that EV charging up to 1000 volt and 400 kilowatt will be facilitated. In case of Tesla superchargers in the US uses their own proprietary charging connector, while the European variant uses the Type 2 Mennekes connector, but with the DC charging built-in. The unique aspect of Tesla connector is that same connector and pins are used for the both AC and DC charging. Tesla now offers DC charging up to 120 kW, and this is expected to increase in the future. Finally, China has their own DC charging standard and connector that uses CEN bus for communication. It has 5 power pins, 2 for DC power, 2 for low voltage auxiliary power, and 1 for ground. This charger has 4 signal pins, 2 are for proximity pilot and 2 for CEN communication. As for now, the nominal voltage are 750 volt or 1000 volt, and the current up to 250 amp is supported by this charger. As you can see, the fast charging is quite alternative in the sense of high power charging with the short charging times. But the fast charging power cannot be increased infinitely. That is due to 3 technical limitations. First of all, high charging current leads to high overall losses both in the charger and in the battery. For example, if the internal resistance of the battery is R, the losses in the battery can be expressed as I power to R for simplicity, where I is the charging current. So the losses increases by 4 times when the charging current is doubled. The second limitation is from the battery. When fast charging the battery, the COC of the battery can only achieve 70 to 80%. This is because fast charging creates a lag between the voltage and state of charge, and this phenomenon increases as the battery is being charged faster. Hence, fast charging is typically done in the constant current or CC region of the battery charging, and after that the charging power is reduced in the constant voltage or CV charging. Moreover, the battery C rate increases with fast charging, and this reduces the battery lifetime. The third limitation is from the charging cable. For any EV charger, it is important that the cable is flexible and lightweight for people to use and connected to the car. With high charging power, thicker cables are needed to allow more charging current, else it will heat up due to the losses. DC fast charging systems today can already transmit charging current up to 250 amp without cooling. However, in the future with current above 250 amp, the charging cables would become heavy and less flexible to use. The solution would be to use thinner cables with cooling and thermal management to ensure that the cable don't heat up. This is of course more complex and costly than to use cable without cooling. To wrap up, In this lecture, the key parts of DC charger have been introduced. We have looked at the different type of DC charging connectors. Finally, we analyzed the various limitations of DC fast charging.